SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 19, we will cover microsimulation and population synthesis. This will be covered in two parts. So, first we will cover part 1 and then in the next lecture we will cover part 2. So, the different concepts that will be covered in this lecture are, of course, the background of microsimulation and population synthesis, cross classification tables, the different steps for microsimulation and population synthesis, major population synthesis techniques, and we will detail the iterative proportional fitting in this lecture. So, in the last lecture, we have covered different methods of population projections. So, whenever we are planning for an urban area, we need to plan for the current scenario as well as for the future scenario. So, that's why we need to project the population for the future as well. Now, one of the methods that we covered was cohort survival method, where the population was broken down into different age groups, as you can see in this image, age group of 0 to 4, 5 to 9, 10 to 14, and also between male and female population. So, one side is male and another side is female, and then the population was projected for the next 10 years down the line or maybe 5 years down the line, by seeing how each age group transition into the next age group. For example, 0 to 4 people belonging to the 0 to 4 age group after 5 years will belong to the 5 to 9 age group. Now, one thing that will change is, of course, some age groups like around 35 to 39, they will also undergo births, and some age groups like 95 to 99, 80 to 90, and there will be definitely some deaths over there. So, that will lead to reduction of the population as well as addition of the population. So, this natural growth is also recorded, and along with that also we will see how the migrant population, what are the age groups of the migrant population, how their birth rate or death rate will lead to addition or decrease of population. So, these all are measured through the cohort survival method. So, one point that we can see is we are breaking the population into different age groups and also gender groups, and as well as we can say that okay, one group is for the existing residents, one for the migrant population. So, when we look at Census of India, we see that the data that is provided in Census of India is based on ward wise. That means, ward is the spatial zone that we are talking about, and the data that we see is the total population, age group wise population, gender wise population, total number of households, household classification, as of course based on the number of people living in that households, based on household size, and car ownership of those households. So, these are the detailed data given for each ward in an urban area. And as you can see that if we want to get the data on both gender and age group, each ward wise, that may be possible, that may be available, that may not be available. But if I ask for car ownership data for each age group, that definitely is not possible from the census. Now, there are some extra tables in census, for example, age group and gender wise data on workers, industry type. So, here we can see that not only gender and age group is there, but based on this particular demographic group, we can also see how many of them are workers and in which industry they are working. So, this could be called as a cross classification table, where we can have detailed data on each population group or each demographic, socio-demographic group in that particular area. Now, as we know that based on our previous discussion on land use transportation problems, we have seen the entire land use transportation problem is divided into many smaller components. For example, there is residential location choice, there is mobility models, then there is location choice model for businesses, and then there is the mode choice models, trip generation models, trip distribution models, and so on. Now, what we have seen also is that primarily disaggregate models are used to determine or predict the outcome of this different decisions, like where will people relocate themselves, or which mode a person will undertake. Now, disaggregate models are called disaggregate because they could be used for taking an individual and then based on his characteristics or based on his household characteristics or based on other characteristics, we can predict the outcome. So, disaggregate models require very high quality micro level and also spatial data. So, this kind of data is not available from census. But as we can see that not only for population projection methods, but also for other kinds of models, we require lot of data which is at a micro level and also which is very disaggregated. So, in this particular slide, we have taken two variables, household type. Of course, we use size as the categorizer for household type, that means what is the size of that household, and then we have car ownership, that means we could have 0 cars or 1 car or more than 1 car. So, these are the car ownership values, and we can determine total number of trips by a family in a particular zone based on these two particular categories, based on each household type and each car ownership, how many trips a particular family makes. And this is relevant. Why? Because the number of trips made by a family depends on the size of that household, and also if the household owns a car, it will be making certain number of trips. If it doesn't own a car, it may be making a different number of trips. So, these are influencing factors. So, if I want to make an aggregate estimate of for each of this household type or car ownership, what kind of trips are made, then we need to create a cross classification table for households in each zone. That means for each zone, if I am predicting what kind of trips are being made, so we will make a table where we have household in one on the as the different columns, and in different rows we have the car ownership on this side and over here, and then we can see that over here the total number of families having 0 cars is 3000, total number of families having 1 car is 540, total number of families having more than 1 car is 135. Similarly, total number of household sizes are 470, household size 1, household size of 2 is 730 and 960 and so on. So, if we see, the census actually provides us with this major data. So, this kind of data is present, but we also want number of households with size 1 having 0 cars, but this data is not there in census. So, we need to determine this sort of data using we need to have certain methods using which we can have this sort of disaggregation, which would be helping us to determine the mode choice of this particular group of individuals. So, that is why even for an aggregate estimate, we need to have this sort of classifications. So, this is called a cross classification table, and if we see this totals of each household type, these are called control totals, because this is through which we can control the total number, the distribution of households in that entire zone, or distribution of households with different car sizes in entire zone. So, these are called the control totals, and as we have, and this kind of cross classification may not be available in census data, which we have already discussed. Now, for a mode choice model for a particular trip in a particular zone, we can either go for an aggregate model or a disaggregate model. Aggregate model means where we take the entire group and we say that, okay, for this type of households, mode choice is this. Or if it's a disaggregate models, we can add other variables as well. For example, we have household type, we have car ownership, we have zone characteristics from where the trip is being made, we have modes available in that particular zone, alternative modes, then mode characteristics of those alternative modes, the trip type. So, these are the variables which we can add, and based on that we can predict the mode choice of a particular household or a particular individual in an household. Now, if we say individual, then again there are two characteristics, like for example, the gender of the individual and the age group of the individual, which may also play a role in the mode choice. So, that means we need to predict the mode choice for an individual of a certain gender, of a certain age group, belonging to a certain household type, also belonging to having certain number of cars for that particular household, and then zone characteristics, modes available, and so on. So, in this case, we can see that not only the household data, but also individual data needs to be combined with household data. And we need to predict zone or ward wise modal choice for each individual as per household and trip type. So, this is what we need to undertake, but we do not have data for that. And so, that is the reason we need to create a synthetic population based on the control totals or marginals. We can call them control totals, we can call them also marginals. And so, based on these values which are available in sensors, we need to create a synthetic population which would have this detailed data, that is like gender, age group, household type, car ownership, and so on, using which we can predict or we can develop a mode choice model, or for the relocation model, or any model for that matters, and that would help us to conduct the entire simulation for this urban area, or that is why we can call it sort of a micro simulation. So, micro simulation is used for predicting the state of an urban area or system by simulating the behavior of the individual actor, which could be either individuals or households, or could be farms, or could be the real estate developer in the system, and in the process assess the impact of current or proposed policies such as travel demand management policies. So, that means when we are doing micro simulation, using that we predict the behavior of each individual, and based on the behavior of individuals we can also see how it impacts the travel demand, or the different policies that we can introduce to manage travel demand. Those impact on those could be evaluated. Now, synthetic population for an urban area is created. As we discussed, there is a need to create a synthetic population. It is created using algorithms which uses categorical or ordinal socioeconomic data sets available from secondary sources like Census of India, District Statistical Handbook in table format. That means, in the previous slide, so we have discussed that we need to have different categories of data, like for example, different household types and different households with different car ownerships and all. So, this kind of tables are available from Census of India data. This is used to create the synthetic population, and using this data, that means these tables that are there, we can create different cross tabulation tables. It could be a one-way table, or it could be, that means only one variable, or it could be a two-way table where there are two variables involved, and it could be a multi-way table involving many variables and cross dependencies. For example, there is gender as well as age group could be a two-way categorization of the entire individuals of a particular area, whereas if we add gender, then age group as well as education, then we are adding 3 dimensions. And when we are adding 3 dimensions, then the dependencies become, there is between gender and education, there are certain amount of there could be, we can develop this control totals. That means we know that there for each gender category and each education category there are certain number of individuals. Then similarly we can do it for age group as well as education, and also we can do it based on gender as well as age group. So, we can have this kind of multi-way cross tabulations, and so when we do develop this kind of tabulations, we can establish the joint distribution. We call it a joint distribution. Basically, these are we know that how many individuals are belonging to each of these groups, so that we can add them up and we get the total group, and accordingly we can also develop their probabilities as well. And so, we call it joint aggregate distribution of demographic or socioeconomic variables. So, if we can create this kind of data or this kind of multi-way tables, this could be used to create a list of all households or individuals, or both in most cases, or farms for an urban area, and for each zone, which could be either a ward or a grid or a TAZ, based on the control totals for each attribute category for that particular ward, grid or TAZ. That means, if we have the total number of values like education, number of people of different education groups or age groups or gender groups in each ward or in each grid or each TAZ, so we can create a list of all households or individuals, where we need to know exactly that, okay, for this particular individual, what is his age group, what is his demographic, what is his education, and what is his gender. So this kind of list could be created. So this is the synthetic population that we are talking about. So we do this, we can create this list by aggregating, we can achieve this by using aggregate data from census, which gives us the control totals for smaller zones, and we can integrate it with a disaggregate data from another source. That means we need to have a sort of detailed data set for, it could be for a different zone, or it could be from one of those zones that we are talking about, or it could be for a group of those zones. So we need detailed disaggregate data which could be gathered from as a sample from the overall individuals of that particular area. So using the characteristics of that particular data, or the distribution of those demographic variables in that particular data, we can create the detailed data sets for each individual zones, for which we only have the total values. So here we say, in case of US, like usually disaggregate data is obtained from sample data sets of the population. For example, in US, public use microdata samples (PUMS) is used, and in UK, sample of anonymized records (SAR) is used. So these are basically surveys conducted by the government, where they collect data from around 1 to 2% of the population, detailed data on their age groups, gender, their household, different properties, or whichever properties the government wants to collect from that particular household or that particular individual. Or these are used, or these are available data sets, but in our country we don't have this kind of data sets. So instead, in our country, whenever a land use transportation model is developed for an urban area, we do collect data from a large sample of individuals, probably we try to cover around 1% or even 2% of the data set, and in form of a travel diary survey for an urban area, and this could act as the disaggregate sample data set in our case. So this includes both individual as well as household characteristics of that particular zone. So or that particular area. So if we have this kind of disaggregate data set, we can use it to construct the detailed data sets for each zone for a particular area, if the totals of those zones are available from census or similar other data sets. So this data, this disaggregate data that we collect in form of a travel diary, or the PUMS data or SAR data. So usually this data has to be, this data is usually not having any spatial information. The reason why government doesn't give spatial information, or rather even if we do a travel diary survey, we should not show the spatial information. The reason is for privacy concerns. For example, if I do a survey of an individual, we shouldn't make sure that data is available which exactly shows that particular individual living in a particular zone. So we usually remove the zone data, zone information from that particular data set, whereas the census data has got the zone information, but in form of totals. So that is why we need to combine both this data. So this disaggregate data is used as seeds to create a synthetic population which are in aggregate consistent with the marginal control totals of the aggregate data, which is the census data. And this data acts as a seed for each zone of this for which we are going to develop the synthetic population. So disaggregate sample data may or may not include spatial information. So if we are collecting travel diary for a particular city, and we have no problems with the privacy issues, that we don't have to deal with the privacy issues, then in that case we have data also zone wise, and we have spatial information, and here only challenge is we need to have a large sample size, so that all demographic groups for each zone is represented, and we can use this data that we collect from the sample as seed data for this particular zone, and using that we can create the entire data, that means the entire list of population for that particular zone using census information. But if we don't have the spatial information, like for example because of privacy issues, so in that case also we can also use this data set and we can combine this, but we will have to use certain other techniques that we will discuss later. So zone location variable can be treated as any other variable like age, gender, etc. So that means we just need the control totals for that particular zone. We just need to know how many households are there in each of this zone or how many individuals are there in each zone. And if we have the data from the census data, using that data also we can create the data, the entire the synthetic population data, or this cross tabulation. We can create those cross tabulations, and even no seed data is available, we can also do that. So the different steps in microsimulation and population synthesis, if we can based on there are different methods to do that. So if we take a look at the different methods and we try to summarize the entire process of microsimulation and population synthesis, then we can divide it into three parts. The first part could be called fitting, the second part could be called allocation, and the third part is of course the microsimulation part. So in the fitting part, we need to construct the household level multivariate table. Multivariate table is the cross tabulation tables. This could be done as per the requirement of the microsimulation or individual models. And then we need to construct the individual level multivariate table or the cross classification table. So this two has to be done separately. We cannot do this two together. And then we come to the allocation part, where using this data in the multivariate tables, we compute the we determine that okay, how we can construct a simulated population or a synthetic population for a particular area. And here we have got multiple steps. For the first step is we compute selection probability of a household for a particular zone grid TAZ. That means we have this disaggregate sample data set. We need to for each individual data in that sample data set, we need to compute the selection probability of that particular sample. So we need to, and that could be determined based on the cross tabulation tables, because in cross tabulation tables we have different demographic groups and we know exact probability of each of this group. And even though we don't have the different probability of each group, we have the marginal totals. So using conditional probability, we can also predict the selection probability of a particular household or a particular for a particular zone. And then we can select a few sample households using Monte Carlo simulation from our list of sample households. That means suppose we have collected for an urban area, we have collected data for 10,000 or 5,000 people. We can select a few of those, and using those selected samples, we can construct the synthetic population of a particular zone. Now, there has to be some criteria. We cannot select them randomly. That is why we need to understand their selection probability. Then using Monte Carlo simulation, which I will explain later on. So using Monte Carlo simulation, we can select some samples from the entire data set, which adheres to this kind of probability. And then we also need to determine the appropriateness of that household, considering zone control totals for both households and population. That means once we select a sample, we need to check that okay, this group that we are selecting is it consistent with the control totals for that particular zone, and that we need to check both for the household as for the population. So once we say that well, that particular selection is appropriate, we can add that selected household to this particular area for which we are developing this particular synthetic population, and we create a household and population list for that area, and we also update a household and individual level count for that each part of that particular zone, and then we repeat the selection of another household. So we do one selection of one household from the sample at a time, and then put them into the target area till the target area is filled, and within that we keep on checking if the control totals are matching in the target area, and also we see that okay, once these control totals are matching, then also we keep record that okay, one particular kind of household has been selected from the sample list, so that next time we can also control the probability of that particular sample being selected. We can reduce that or we can keep it as same depending on different strategies. So the third stage is of course the microsimulation stage, where once we have created a list using this allocation strategy of synthetic population, then different components of urban land use transportation model like residential mobility, location choice, trip generation, destination choice, mode choice are simulated using household and population list for each zone. So this is the microsimulation part. So microsimulation and population synthesis goes hand in hand, and the quality of microsimulation that we can do in an urban area depends on the quality of population synthesis. So the better is the population synthesis, better is microsimulation for that particular area. So some of the major population synthesis techniques are iterative proportional fitting and synthetic reconstruction technique. So IPFSR we call it, and there is also combinatorial optimization technique, which is the CO technique, and in addition to that there are several other techniques like iterative proportional updating approach, Markov process based approaches, and also there are a lot of other emerging approaches, but in this lecture we will focus on this first two techniques, iterative proportional fitting and combinatorial optimization. And these are the different techniques that are used, but there are several softwares also in use, like for example PopSynWin. This is a software where household selection probabilities are used to control person level constraints. This is used in Chicago, Illinois. Then there is a PopGen software. This is a popular software where it's a standalone software package for US. It can fit households and personal level marginals simultaneously using a novel technique. Then there is ILUT, Landuse transportation model. Here a sparse list structure is used. I will explain what is sparse list later on. One entry per unique combination of attributes, and this is used in Toronto, Canada. Then in SameDep, we use it combines multi-way contingency tables. That means different tables could be combined over here. In Albatross, which is used in Europe, and which is also another land use transportation model that we have discussed earlier. Here household distribution is estimated from person level distribution, and this is another, it's another method which use different variants of iterative proportional fitting, and this also will be discussed in the next lecture. So now coming to iterative proportional fitting and synthetic reconstruction technique. So we will first cover the iterative proportional fitting part. As you know that this IPFSR technique is in two stages, fitting and allocation, and we will cover the iterative proportional fitting part, and this was introduced in the year 1940 by Deming and Stephen, and here contingency tables of attributes of agents sampled from a region is available with marginal totals. This data has to be available, and for individual zones only marginal totals are available, and then using the IPF algorithm we have to create a multidimensional contingency table or cross classification table of attributes of households, and we can also do it for every zone, and we just have to make sure that the number of agents in a given category matches the corresponding marginal sum and the correlation structure of the seed is retained. That means the correlation structure of the seed is retained means, for example, we have a target area and we have the sample data set which we call the seed data set, and here these are the marginal totals for this column, these are the marginal totals. For these two rows, these are the marginal totals, like a cross classification table. We also have the group, the number of people in each of these groups, that also we have got. So this is the seed data, and we need to apply it in a target area where we just have the control totals, but we don't have the grouping. And this control totals, for example, the sample may cover around 10,000 people or 1,000 people, whereas this zone may have 1 lakh people. So we need to clone this population for this entire zone. So that is what we are doing over here, and using IPF algorithm helps us to do that. Like we have the entire study region, we do the seed data collection in the entire area, but we only do it for 1% of the population or maybe even less. But then for each zone we need to detail out this using this seed. We assume that the same correlation structure of the seed would be retained for each of these groups, and we detail the total population of zone 1, zone 2, zone 3, and this is for, and for each zone we have the marginal totals, and we can estimate the values of each of these demographic groups, and this is where the IPF algorithm comes into play. So In IPF algorithm, for each control variable, the corresponding slice of the contingency table is scaled proportionately, so the total number of agent matches the control total in the target table. Now, there are few things that we need to be careful about. For each control variable, that means in a contingency table, like over here in the previous one, this is one control table value, this is another control value, these are the row values and these are the column values of the control. So, that means we have to see that each of this matches with the after we do our algorithm, this has to be matched. So, for each control variable, we need to modify the contingency table by proportionately we need to modify it, so that the total number of agent matches the control total of the target table. So, that is why if there are several iterations, if Pk is one iteration, k is iteration number, ij is the matrix element in row I and column j, and qi is the row sum and qj is the column sum. These are the target these are the target control totals for row for each row, and these are the target control totals for each column, and then we can estimate the matrix cell values iteratively using these two formulas, where we see that okay, this is the control total and this is the actual value of a particular cell, which we need to modify proportionately by summing up the values of all the jth columns in that particular row, and then we can divide take the qi value, this is the target value, divided by the summation of this, and then we need to multiply with the actual value in the seed table to arrive at the target table. So, once we do it for row, we need to do it for the column. So, we need to take one direct, I will explain it with an example in the next slide, but we need to go for each control total one by one. So, first we need to take care of the rows and then we need to take care of the columns, and all control variables are iterated one after another. So, we do it one after another, and once we have done that, then we repeat the entire step. So, this is again repeated and each step is called an iteration, and iteration will be carried on till the relative error of the distribution versus the marginal sums reaches a user specified threshold. That means, we decide how much we will iterate this, keep on iterating based on the amount of accuracy that we want. That means, as soon as we do this estimates, we will see that the values of the existing seed table is changed and we are gradually approaching the target values. But it cannot be achieved in one iteration, it takes certain iterations, and the amount of accuracy we want has to be determined by us itself. So, in this particular example, you can see we have got a classification table. This is the seed data for from the sample population that we have maybe we have surveyed for a particular area. We have household size for 1 member households, 2 member households, 3 member households, and more than 3 member households. And similarly, we have car ownership data for 0 car households, 1 car households, and more than 1 car households. So, we see that these are the totals for each of this group, and these are the seed data. That means, we have from our sample survey, we have found that we have 16 number of households which has got 1 member and 0 cars. Then we have 6 number of households which have got 1 member and 1 car, and so onwards. So, total number is 130. So, this has to be consistent. So, this when add up and this when add up, both has to be 130. Now, we have a particular zone where we just know the marginals. That is, we know that there is 100 0 car households, we have 90 1 car households, we have 110 1 car households, and so on. And we have 91 member families, 82 member families, 63 member families, and 73 member families, which also leads to 300, which also needs to be consistent. So, the next step is we need to determine using this particular formula that qi value is 100. So, over here this is the qi value, this is the marginal total that we need to achieve, and then we see that when we sum up the pkij values over here, we see that together it is only 50. So, that means when we estimate this, qi is 100 and this is 50. So, this becomes the proportion, which is 2. We need to multiply 2 with pk. Pk is 16. So, this becomes 32. So, this is, we have to do it for each row one by one, and then we arrive, when we do that, we see that the totals become same as the marginals, but the other side it is not the same. So, there is some discrepancy. We cannot see that this 90.125 is not same as 90, 100 is not same as 80, and so onwards. So, in the next step, we need to modify the totals for the columns. That means, over here we have we determine the column adjustment factors. In the same way, we determine that qj is 90, like for example, for this first column it is 90, and then we sum it up for ij for the first, after the first iteration k plus 1, we sum it up for each I, and then we find that this value is 90.125. So, again we determine that the total the proportion, that is qj divided by summation of pk plus 1 ij for each I. Here we see that the factor becomes 0.9986. That means, using this factor I have to multiply each of the cell values in this particular column, and we get this new values. So, this is end of iteration 1. So, here we see again the columns match, 90 matches with 90, 80 matches with 80, because we are proportionately matching them, but this has got changed. So, this is now different from 100, 87 is different from 90, 101 is different from 110. So, in the next step, we will keep on doing this iteration in step 2, step 3, step 4, and we keep on doing this, and we will keep on doing this till we see that okay, the total difference between the values that we are getting from each cell and the actual values that are supposed, or with the marginals, the value is such that it is within acceptable limits. So, we have ended at iteration 4, but probably we should have gone till iteration 7 or 8 or 9, probably then we would have got more accurate results, because here again you see that the total values we are getting is 100 while this matches, this side we are getting 100.03, we could have further reduced this to 0.003 or 00 some value, so that we require some more iterations. And once this iteration is completed, here we have already multiplied the proportionate, the actual value from the seed with the proportion that it should be multiplied with. But if we have not done that, we could have kept it in proportional form as well. So, that means that this is sort of that is the proportion of that particular group within the total zone. And then once we have this kind of values, we need to integerize it. That means, we need to convert this to integer. So, over here we did a straightforward integerization, where we are finding that 27.9 becomes 28, 17.1 becomes 17. So, this values comes over here, and we see there is a little difference with the marginals. Like here we are getting 100, but here we are getting 91 and 111. So, that is resulting in addition of 2 people. So, this is a discrepancy. Now, for example, in this particular example, this may not look too much, but when we have lots of categorizations, when we have very, very small groups, like for example, each group having only 3 or 4 households, and we have lot of categorization, this value becomes very, very important. So, integerization has to be done very carefully, so that we don't overemphasize or overestimate certain groups in a particular population. So, as we have seen that marginals can be single, that means this is a single marginal, that means we have to match these values, total values, and this are a two-way. If we need to match this sort of values where both the factors are required, like over here, if this becomes a marginal, then we will call it a two-way marginal. That means 2 factors has to be matched. So, marginals could be single dimension or multidimensional, or 2-dimensional marginal for attribute m and n can also be treated as a single dimensional marginal, that means m into n of Cartesian products. Similarly, higher dimensions can also be converted. What it means is, if I have age and age groups and car ownership, we can have a new group like households with age group of or an individual with age group and car ownership. This can become a new group, and that together m into n together becomes one group. And if we have the seed data for that, we can also use that to convert higher dimensional marginals into single dimensional marginals. So this is that means we can solve very complex groupings also in very simple form, but also it means also that we need to have those kind of seeds in the data for our sample data as well. Similarly, multi-dimensional control totals can be easily converted into single dimensional controllers with more categories. That is understood, because if we can convert it like this, for multiple dimensions could be converted into a single dimensionals by multiplying this two or combining these two dimensions m and n. And IPF, then the next issue is with IPF is IPF can estimate only one level of aggregation. That means agent level or individual or group level, or that is household attributes, but both cannot be done simultaneously. That means we can match the agents, individuals in a zone with the control totals, or we can match the households in a zone with the control totals, but we cannot do them together. One strategy could be to convert all agent level attributes into group level attributes and then apply IPF at the group level. So that means one strategy to overcome this problem is, we don't do it for the agent level, we only do it for the household level, and we first convert every individual into groups and we assign them, we make them into certain number of households, and then we proportionately determine the households, and when the households are determined, automatically the number of agents in each group could be determined from the households itself. Another issue is with IPF is, IPF could be done zone by zone. That means for each zone we can do an IPF, and then we know that exactly for each zone what sort of using control totals of each zone we can determine what sort of people, what sort of demographic groups should be there in each zone, but we also require the disaggregate sample data to have seed data for each zone. Or it could be a multi-zone approach, which means that first agent groups can be estimated for all zones simultaneously by adding a control total for each zone, and then we can determine it for each zone. That means first we determine the IPF for the entire urban area, we determine demographic groups for the entire urban area, and then taking zone as one level, adding another level, we can again divide this population into different zones. So since in most cases zone wise seed data is not available, we use seed data as one, or that means any equal seed data would be fine. So that means we use a seed data, because we don't have seed data, we assume that we use a matrix of we use a matrix with each cell having one value as the seed data, and using iterative proportional fitting we can arrive at number of population in each zone. I will demonstrate that. So in this example you can see that we have taken a higher dimension m into n. So we have increased the number of groups from the last example. So there are three categories of m and 2 categories of n. So that's why we have groups like 1 1, 1 2, then 2 1, 2 2, and 3 1, 3 2. And we have got 4, suppose we have got 4 zones. Now as I told you, zone could be also taken as a particular category, like same as like a number of cars, or same as like age group, it could be taken as a category. So we can proportionately, if I have the seed data for this particular each of this zone, as I can see over here, so using the same IPF procedure we can estimate total data in my target zone. These are the target zone marginals. For each zone we know how many people are there, for each of these groups we know how many people are there. So using this marginal data and then our control total, and using this seed data we can easily calculate the IPF like following the same steps, and we can arrive at this particular result. So this could be called the zone by zone approach, where we have seed data for each zone and we can estimate the population for each zone. Or it could be a multi-zone approach, where we don't, let us assume that this seed data is not available. So, here what we do is we take this seed data is available, but for this is the total seed data for this sample population, not for each zone. And like for example, in the previous case, we assume that this is the seed data for this particular zone, but over here we have the seed data, and here we make the initial data value as 1, and this, following the same procedure, we can arrive at the proportion of people or households in each of these demographic groups, following the same IPF procedure. So, this is called the multi-zone approach. So, these are some of the references that you can follow. So, to conclude this lecture, we can say disaggregate models require high quality and highly categorized spatial data which are not available directly from standard data sources like Census of India. Sample surveys are conducted to collect data at a desired level of categorization, which can be used as a seed to generate synthetic data for other zones or regions. Then population synthesis is conducted in 2 steps, namely fitting and allocation. Fitting is shown in this particular lecture, allocation will be taken up in the next lecture. And iterative proportional fitting is the most popular fitting technique adopted in most population synthesis software. Thank you.